Okay, so I'm going to be talking about how can we better control wind turbines and wind power plants so that we can integrate higher and higher amounts of wind energy on the utility grid without worrying about the reliability of the grid. So as most of you probably know, wind energy has been increasing in installations worldwide at a pretty healthy rate. It's one of the fastest growing sources of our electrical energy needs. And over the last decade or so, worldwide installed capacity has been growing at an annual rate of about 25% since 2002. And now, at the end of 2013, we're at over 300 gigawatts of installed capacity worldwide. Now, if we look at just the European Union, okay, which is where giving the talks, I'm trying to draw some data from Europe. It's had a slower growth, but still very healthy, about 16% annual growth in installed capacity since 2002, and they're now at above 106 gigawatts of installed capacity. So in 2002, they had about 75% of the world installed capacity. Now they have about 35% of the world installed capacity. So the growth in installed wind power has been more elsewhere in the world. Now let's take a look at installed capacity around Europe. So Germany and Spain are the two countries that have the most installed capacity, and a number of other countries, including Italy, have very healthy installations. Some of these countries have only started to install wind power plants in recent years and are actually installing them at quite rapid rates, so they will probably catch up over the next decade. Now let's take a look at the top 3 countries in installed capacity. So who knows which country has the most installed capacity? In China, yes. So China in 2002 only had about half a gigawatt of installed capacity. They've had an annual growth rate of 70% on average since 2002, and now in 2013 they've exceeded 80 gigawatts of installed capacity. Now, which country do you think? Yeah.
Excuse me, Lucy, how do these numbers work out in terms of percentage of the entire power, or am I stealing your thunder?
Of the entire
power used in the country?
Oh, so I will get to that in a little bit. Yeah. Yeah.
Here, a set of data which shows the amount of gigawatts produced per capita per solar PV.
I don't think I have that data in particular, but yeah, that talks about the density. And China is obviously going to be lower in that regard as well.
I'm thinking of the Netherlands, I saw some density numbers and they were pretty high.
Yes, yeah. So I don't have the density data. Okay, so which country is second in terms of installed capacity? US, exactly. So US now has over 60 gigawatts of installed wind capacity. We've had an annual growth rate of 30% every year since 2002. So in 2002, we had maybe 10 times the installed capacity of China. We've grown at a slower rate, so China surpassed us in 2010. Now, which country is number 3, do you think? Australia? No. Okay. Germany, yes. So Germany has only grown, still at a reasonably healthy rate, 10% annually since 2002 on average. They now have over 30 gigawatts of installed capacity. They had about 25 times installed capacity compared to China in 2002, about 2.5 times what the US had. They've grown at a slower rate since then. So several European countries are like that. They had more installed capacity about a decade ago compared to other countries, and they've grown still at a healthy rate, but not as fast as some of these other countries. All right, so now another way to compare, so maybe before I get to that, I think I have one more slide showing more countries. So after China, US, and Germany, we have Spain. India, like China, has seen rapid growth in recent years. A number of other countries in Europe, Italy, where I'll be next week, is about 7th in the world. Canada has had a number of strong years in installations recently as well. So now getting to wind penetration, that's another way to compare countries. And so what wind penetration is, it's the percent of each country's electrical energy needs that is being met by wind, okay? And in this regard, Denmark is by far the #1 country. So about 30% now of Denmark's electrical energy needs are being met by wind. Okay, so if here circle the 3 countries that we talked about earlier. China, even though it has the most installed capacities, actually has lower wind penetration. Okay, so a number of European countries have quite strong wind penetration. US is at about just over 4% right now. Okay, so the wind industry overall is relatively healthy. There have been strong growth in installations worldwide, but the wind industry is continuing to try to drive down the cost of wind energy to try to make it more and more competitive with other sources of energy. Okay, and one way that it tries to do this is to go to larger and larger wind turbine sizes. So if we look at the wind turbine sizes over the last 3 decades, they've really grown. So wind turbines that are typically installed on commercial wind farms now are in the megawatt range. They typically are at about 90 to 100 meters at hub height, and they typically have rotor diameters of about 100 meters. That's hard to fathom. It's, when you see a wind farm far away, they don't look that large until you get very close up. So I've put 2 other things on here at approximately the right size. So Boeing 747 is noticeably smaller than the current rotor area of. Yeah, so that's a soccer field, since I'm going to be in Europe next week. And so these are really large machines. So for land-based turbines, the commercial wind farms that are being installed now tend to have 1 to 5 megawatt wind turbines being installed. These larger turbines that are under development are more for offshore wind, because for land-based turbines, in terms of the size of roads, the size of railways, they're really reached capacity in terms of the sizes of wind turbines that they can install. So these larger turbines are being developed primarily for offshore wind. Now you might say, well, why are they developing larger wind turbines if they're so hard to transport? Well, the primary reason is that the power available in the wind is proportional to the cube of wind speed, and wind speed tends to increase as you get higher off the ground, and so that's one reason to go to higher and higher towers. And the power is also proportional to the rotor area, so that's another reason to go to larger turbines. All right, so let me just briefly, in a nutshell, explain wind energy. So wind comes into the rotor plane, and because of the design of the blades, that creates lift, causing the rotor to spin. Okay, that causes the low-speed shaft to spin, and that typically is stepped up through a gearbox to a high-speed shaft, which will spin the generator generating electricity. So I have kind of a model turbine, which I'll pass around just for fun. So the main components are, there's the base, that's usually a lot of concrete, the tower, and then the nacelle, which sits at the top of the tower and holds the generator, and then the rotor, which includes the 3 blades and the hub at the center. And so this is maybe a 1/200th scale turbine compared to a megawatt wind turbine. I have other ones, yeah.
So Lucy, I in your talk can talk at all about these turbines without gearboxes, bringing in solar wind power and that marsh.
Yeah, so I'm not going to talk about direct drive, but yeah, Sandy Butterfield gave a very good Rasei talk, which I think was recorded, so I think it should be online, about the direct drive.
I wonder for your presentation, I'm taking it up.
No, I'm not going to talk about that. Okay, so let me talk about the 3 main operating regions of wind turbines, and I'm going to talk about these in terms of an example 2.5 megawatt wind turbine. Okay, so here we're plotting power as a function of wind speed, And this first blue-gray curve is the power available in the wind. So it goes up as the cube of wind speed. And this dark green curve here is the ideal expected turbine power. We'd like the wind turbine to be generating power following this curve up as wind speed increases. Now, when wind speeds are too low, so less than 6 meters per second here, so the conversion from meters per second to miles per hour is about 2.2, so 6 meters per second is about 13 miles per hour. And so when wind speeds are lower than that, for this example, it's considered that due to friction and bearing losses, it's not worthwhile to be generating power from the wind turbine. So only when the wind speeds get high enough, past this threshold, do we move into what's called region 2, or it's also known as below rated operation. So now in this region, we'd like to follow up this curve. So this is also a cubic function of wind speed. We'd like to follow up this curve to try to maximize power capture of the wind turbine. And in commercial wind turbines, there are variable speed machines, and they typically will try to vary the speed of the rotor to ensure that it's operating at maximal aerodynamic efficiency so that you can maximize power capture. So for commercial wind turbines, typically the power coefficient, or typically the fraction of wind power that you can capture, is about 40%. Okay? Now, as wind speeds continue to increase, we will move into what's known as region 3, or above rated operation. So now once there's enough wind speed, now we're actually capturing already 2.5 megawatts of power. We're generating 2.5 megawatts of power. And we don't want to generate any more power because we'll burn out the generator. And so in region 3, what's done is to pitch the blades to let more of that wind go by. So we're shedding some of that wind so that we can maintain the power capture at the rated power of the turbine. And we also try to pitch the blades to additionally try to mitigate structural loads on the turbine, okay, to reduce maintenance issues and extend the lifetime of the turbine, all to try to reduce the cost of wind energy. Now, so this is typically how wind turbines are operated. So in region 2, you try to maximize power capture. And in region 3, you're regulating the power at that rated power of the turbine. So effectively, in both these operating regions, region 2 and region 3, you're operating at the maximum power that you can be. So here, you're trying to maximize power, and here, you're at the maximum power, rated power of the turbine. And so the concern with having more and more wind power on the utility grid is that wind turbines typically can't increase their power to help address electrical load issues that might occur on the grid. And so what I'll talk about later on in the talk is, talking about can we or should we derate the power being captured by the wind turbines so that then there's headroom that allows wind turbines then to respond to utility requests for more power to try to balance the grid. Right? So before I talk more about what's called active power control of wind turbines, let me talk about the operation of the utility grid. I'll first talk about it more generally, and then talk about some of the challenges as we increase renewables, in particular solar and wind, on the grid. And then I'll talk about some of the solutions that can try to address some of the issues. Okay, so just a very brief history of power systems. As power systems were built up, as there are customers, typically there's power that's generated at a power plant, and it's transmitted, often over long distances, to a local power substation, which then distributes the power to the customers. Okay? Now, most traditional power plants have what are called synchronous generators. Okay? And as power systems were built up in different geographical regions, ultimately they were connected for improving the reliability, so that if one region had greater electrical demand, the power systems from other regions could help provide that generating capability. Now, when synchronous generators are operating at nearly the same frequency and they get interconnected, they tend to synchronize with one another. They tend to swing together at essentially the same frequency. Large deviations can in the frequency can destabilize the network of these connected generators. And so we typically don't want large deviations in frequency. So I want to thank Jacob Aho, my PhD student, for this slide. We've used it a number of times to try to explain this concept in a fun way. So the grid frequency fluctuations are governed by the swing equation. PG is the power being generated. PL is the electrical load. So we want the power generated to equal to the electrical load. Okay, so when it is equal, Mr. Conventional Bear is happily pedaling on a flat surface, and the right side here is 0, and so the frequency of the grid is constant at the desired frequency, which in the US is 60 hertz, in Europe is 50 hertz. M here is the inertia of the system, or it's proportional to the inertia of the system. So we'll talk about that in a bit. Now, if electrical load suddenly increases relative to the power generated, then this right side becomes negative and the frequency drops. Mr. Conventional Bear has a harder time going uphill here, slows down. Now, if the electrical load drops relative to generation, then this right side is positive and the frequency of the grid will increase above 60 hertz. Now, it's probably more common that electrical load increases, or sometimes a generating source will have a fault and drop off the grid. And so oftentimes we want to respond to events such as that. So if we have a loss of generation event, okay, PG drops and the grid frequency will suddenly drop. Now, how fast this frequency drops depends on this system inertia. Okay, the larger the system inertia, okay, you can think of dividing this equation by m, so this comes to the right-hand side. So the larger the system inertia, the smaller the magnitude of this slope in this drop of frequency. Now, primary frequency response is this first period where the synchronous generators, via their governors, provide an automatic response to try to arrest the frequency drop and then bring it back up to some steady state. And this all occurs in about 30 seconds. Now, once we complete the primary frequency response, then it's transitioned to what's known as a secondary or tertiary frequency regulation period, where there might be automatic power commands generated through an automatic generator control, or manual power commands generated. And the goal here is to bring this frequency back up to the 60 hertz in the US or 50 hertz in Europe. All right, so let me talk a little bit about primary frequency control and secondary regulation. So in the industry, this is typically referred to as primary frequency response, but in electrical engineering, we talk about frequency responsive systems, and so it can get pretty confusing. And so I like to refer to this as what we're really doing is doing primary frequency control. So that's how I'm going to refer to that for the rest of the talk. I might also call it droop control. Okay, so we're essentially trying to arrest the frequency drop and bring it back to some steady state here. And this is for synchronous generators provided via governors. And the governor response is characterized by what is called a droop curve. That droop curve is typically fixed for the mechanical synchronous generator machine. Okay, so what a typical droop curve looks like is as follows. This is a plot of the percent change in commanded power as a function of grid frequency. And so if the grid frequency is close enough to 60 hertz within this deadband, then everything is happy. Nothing actually is activated in this primary frequency control. But if the frequency deviation gets large enough that we move out of the deadband. So in the US, it's common to see deadbands of plus or minus 15 millihertz or plus or minus 30 millihertz, kind of in that range. And so if, say, we have a sudden loss in generation, grid frequency will drop, and if it drops enough, then we come to this droop region where it's going to command an increase in power from this generator to try to arrest that frequency drop. Okay, so essentially it's a proportional control in this region. Okay, so because this is being plotted as percent change in commanded power as a function of grid frequency, the smaller the percent droop, the more aggressive the droop curve. So a 3% droop means that a 3% change in grid frequency leads to a 100% change in commanded power. So if you have a 1% droop, then a 1% change in grid frequency will lead to a 100% change in commanded power. So it's more aggressive. All right. Now, secondary control is a little more complicated to explain. There are many different ways that and different details in different utility systems. So I'm not going to go in as much detail here. But the goal here is that after the primary frequency response, we want to bring the grid frequency back up to 60 hertz, say, in the US. And what's typically done is, based on measurements, an area control error is computed, and it's a function of frequency errors as well as power flows. And so this ACE signal is a function of this frequency error. Beta is a gain that's often referred to as a frequency bias. And this is the actual interchange power flow, and this is the scheduled interchange power flow. And so if there's an error there, that's accounted for in this area control error. And so the automatic generator control generally implements a pretty simple control algorithm, often a proportional integral derivative controller or a logic controller, to drive this ACE signal, the area control error signal, to 0. And so that effectively will essentially drive the frequency to the desired frequency of 60 hertz. Usually, the automatic generator control sends a new regulation power command every 2 to 4 seconds. Right? So to recap then, we want electrical generation to be equal to electrical load. And traditionally, what's done is the electrical generation is controlled to follow the varying load. The utility typically doesn't know when you're going to use your different appliances or lighting, or when that factory is going to go into full production and such. And it's just trying to adjust generation to meet varying demand. So in order to do that, it has to have some operational reserves. It can't always be operating at maximum output. Okay? And if there's imbalance between electrical generation and load, that will lead to frequency variations on the utility grid. If there are large imbalances, that will lead to large frequency fluctuations, which can lead to sort of unwanted, under frequency load shedding, so just dropping electrical loads, or even blackouts. All right, so now let's take a look at how do utility grids try to vary generation to meet load. So a typical system load across a 24-hour period, across a day, might look like this. So from midnight to 5 a.m., there's not as much load. And then as people get up, turn on their lights and appliances, then there's more load during the day. And then in the evening, as people go to bed, load drops again. So a lot of utility might have some amount of nuclear, which they operate. They might have some amount of coal. Okay, so ideally, they'd like to just have nuclear and coal be operating at some fixed rate of energy production. There might be some hydro, and then oftentimes gas is the most flexible, so that's the one that gets cycled up and down to try to meet increases and decreases in demand. Now, what happens when we have increasing amounts of wind and solar in the generation mix? Well, wind and solar are intermittent generating sources. Wind energy is only available when the wind blows. Solar energy is only available when the sun shines. And so people are worried that as more and more wind and solar are integrated onto the utility grid, that these intermittent sources are hard to predict, hard to control. It's going to be harder and harder to control this generation mix to meet variable load. Okay? And wind turbines typically, and similar can be said about solar, they're typically decoupled from the utility grid through their power electronics. So they're usually not asked to provide primary frequency control or secondary automatic generator control. And as such, as more and more wind and solar are added to the generation mix, the remaining traditional sources are asked to do more and more of the balancing work. So now the remaining sources of energy are now becoming smaller and smaller percentage of the generation mix, but yet they're still asked to do all that balancing. And so there's worry then that it's just going to be too hard to balance generation with load. In particular, also, if we look at more and more electric vehicles on the grid and looking at sort of peak demands that might come about. So as there are more electric vehicles, say 1 million electric vehicles, that might, at the end of the day, people have commuted to work and back. They all plug in their electric vehicles. There might be this sharp increase in load that might be difficult to try to meet that demand. And so there are concerns over the reliability of the utility grid from many different viewpoints. So let's go back and take a look at this again and look at changes due to wind energy. Okay, so this is the system load as before. Now suppose that we have wind energy and we're going to take all the wind energy that is available, since wind is a free fuel, so when it's blowing, let's use it. Okay, so say we use wind energy as we can, and that essentially decreases the system load that must be met by other generating sources to this green line now. Okay, so if we look at what we had before, so wind typically blows harder at night in most regions around the world, and so there's kind of a bigger decrease here and maybe a bigger decrease in the evening, and maybe less so during the daytime. And because of this decrease, now we're asking hydro to cycle, and we're also asking coal to cycle, and if we increase wind penetration further, we might ultimately need nuclear to cycle. And so this is some of the concern, is that it's difficult for coal to cycle rapidly to respond to changes in system load. All right, so what are some methods that we can try to address these issues? So one method is to try to do load regulation, or what's also called demand response or demand side management. Essentially, kind of predict what might happen during the day. So if it's predicted to be a really hot day in the summertime, you might, while it's still early in the morning and not a lot of demand, you might start to cool down buildings more than you would at that time of day, but just use that thermal inertia of the building, cool it down. Most people can't feel the difference in a few degrees, and so then the air conditioning might not be required during the peak part of the day, and so that helps then to reduce that peak demand and help the reliability of the grid. There's a number of people in our field that have looked at demand side management, time of use pricing, and they've also looked at optimal pricing strategies so that users will do the right thing and try not to increase the electrical load at what would otherwise be extreme peak times. Another way to try to address some of the issues of increasing renewables in the grid is to try to develop effective energy storage techniques. Unfortunately, at the current time, the most effective electrical energy storage methods are really expensive, so it's not really being embraced as the solution just yet. People in our field, there are some that have looked at better modeling and control of storage options, also looking at where do you place the storage at different locations on the utility grid for maximizing effectiveness. They've also looked at, suppose that we do have 1 million electric vehicles. While it can be viewed as a load, they all have batteries, so they can also be viewed as a supply. And so how can we, if we had smart meters and distributed controllers on these electric vehicles as they get plugged in at the end of the day, as long as the user doesn't care about their vehicle being charged until the next morning, then let the utility decide how to charge that vehicle, possibly drawing energy from the vehicle if needed, when the user doesn't necessarily need that energy. And finally, what I'd like to spend the next little bit talking about is active power control of wind power plants in particular. And you could do the same for solar as well. So the idea here, I already alluded to earlier, is that instead of operating wind turbines and solar at their maximum power capabilities, let's derate them, say, to 90% or some level, so that we leave ourselves some headroom so that we could increase power or decrease power to respond to utility grid requests to help balance the needs there. So there's been more work that has been done in developing active power control methods for wind turbines. It's a relatively newer area of research in the solar community, but Professor Maximovich and Andy Hoke are actively looking at active power control of solar as well. Okay, so before I talk more about active power control of wind in particular, I just also want to make a brief comment that wind forecasting has been improving. This is largely being done by the atmospheric science community, and they have been developing better and better methods of wind forecasting such that, and as these utility grids change the way that they operate to be more flexible in planning sort of 5 minutes ahead, in shorter time increments ahead, that, along with better forecasting, will mean very accurate forecasts and better reliability in terms of scheduling wind that will actually be available and be provided. Okay, so let me now talk just a little more about active power control of wind turbines. Can we actively control the power of wind turbines, not always to be at the maximal level, but to be at some lower level, and then can we control the power of wind turbines to follow a desired power reference so that we can help stabilize the grid and possibly make it more reliable? Okay, so wind turbines, as I mentioned, are traditionally decoupled from the utility grid, so they're typically not asked to provide primary frequency control or secondary regulation. But wind turbines can we can implement a droop curve synthetically via software and ask a wind turbine essentially to respond to frequency deviations. Okay? Now, in fact, for wind turbines, we have more flexibility. So with synchronous generators, they typically have a fixed droop curve that's tied to the physical characteristics of that synchronous generator. But for wind turbines, we can design different types of droop curves. In fact, what we found is dynamic droop curves, time-varying droop curves that change their characteristics over time, in particular as a function of the rate of change of frequency on the grid, tend to actually be very effective. Okay, so just as an example, so if the rate of change of frequency in the grid is 0 or very little, we might use a very non-aggressive droop curve. So here what we have is we have two static droop curves. Static droop curve 1, which is this red curve. It's less aggressive. It has a 5% droop with a 50 millihertz deadband. And then we have a more aggressive droop curve, static droop curve 2, that has a 2.5% droop. Okay? And what we do for our dynamic droop curve is we interpolate between the two based on the rate of change of frequency. So if the rate of change of frequency is 0, then we use the less aggressive droop curve. And if the rate of change of frequency starts to increase in magnitude, so it becomes more negative here, so we have a drop in frequency, then we interpolate between the two static droop curves to generate our dynamic droop curve response that we want, and we can go more and more towards the more aggressive droop curve depending on this rate of change of frequency. Uh-huh.
So what are you controlling to change the droop curve? The pitch, the blades?
So, okay, so the droop curve takes the frequency input. So depending if the frequency drops, okay, then we will have a commanded power. Okay, then that commanded power is sent to our control system for the wind turbine, and we change both pitch and generator torque to try to follow that power reference. If the power reference is not changing too rapidly, we can typically follow that just with pitch alone. If the power reference changes more rapidly, generator torque has a faster response, so then we'll use that to follow the power reference. Okay? All right. Mike?
So you went to a 50 millihertz deadband. Do you have that degree of freedom?
Yes, we do have that degree of freedom in terms of what we're asking out of our wind turbine.
But it's not the grid doesn't constrain you.
The grid doesn't constrain us. So usually for synchronous generators, there's just some fixed droop that's tied to the physical characteristics of that synchronous generator. For wind turbines, they're typically decoupled from the utility grid due to their power electronics, but we can ask for them to provide a primary frequency response through a synthetic droop curve, essentially. Okay? Any other questions?
You know, some time ago we had this fellow from England gave a discussion on this. Is that what they are trying to develop in England?
Yeah, I know, yeah. I was there, and I forgot the TV. He came last fall.
About a year ago.
Yes. He's from Sheffield. And
Yes.
I know you were there too. I've forgotten the details of what he was talking about. Yeah.
Controlling them to look like a synchronous generator, basically?
Yeah, he was using inverters, right, to kind of emulate the grid. Yeah, right.
So there's a lot of similarities to this.
Yeah. Okay. All right. So we've run grid simulation results to see how well wind turbines can respond to grid events using a dynamic droop curve. So here we use an IEEE standard grid model. And in the simulation here, 5% of the generating capacity suddenly goes offline, just drops offline at time is equal to 1,000. Okay, so when there's no wind in the mix, this is the response. So just all conventional generating sources. Now, if there's 15% of the utility generating sources is now wind, but if wind, as it traditionally has been, does not participate in primary frequency control, then we actually have a worse response. So the frequency drops to a lower nadir and comes back to a steady state that's further away from 60 hertz. Okay, this makes sense because only 85% of the generating resources are trying to respond to this grid event. Wind is not trying to help there. Now, if we let wind participate with the dynamic droop curve, then we can actually do better than when there was no wind on the grid. Okay, so we're arresting the frequency earlier and bring it back to a steady state that's closer to 60 hertz. Okay, and this then leads to the secondary control having an easier time. Yeah, Frank?
To what extent in the normal system is the droop associated with the total size of the power system? Since the generators should couple together, you've got all this timing. So am I correct that the droop curve that you typically see is kind of a function of the whole system size and response? Or is it only separated to an individual generator? Certainly,
it is tied to the particular generator, but they will all, do you know?
Well,
okay.
You can look at the whole grid, it has its droop curve. That droop curve is flat, horizontal. And then each generator has its droop curve that plays against it. It cannot change this flat curve. And that is in fact used for a historical generator. And that leads to what's called the house diagram. And I think if you have power people in the audience, they may use that terminology.
Okay.
That's only if you're assuming that your generator is significantly smaller than the grid and can't actually affect this frequency.
That's right.
Right. But we're trying to, yeah. So we're assuming that we have grid frequency data that we can use to generate a power reference curve to provide to our wind power plant or our wind turbines. And then we're trying to design the controller for the wind turbine to follow that power reference.
Lucy, one more. To give me some sense of how significant this improvement is. Can you quantify what is the negative impact of 100 millihertz or 200 millihertz droop from the 60?
So it depends on the particular grid and the utility, the generating mix on it in terms of how low is too bad. But typically there's some threshold below which you'll have load shedding, and that might lead to blackouts.
So there's almost a catastrophic change.
Yeah, so there's definitely some threshold at which point, there is a catastrophic change. And so you want to arrest this, as much.
And this is significant enough with respect to.
Right. And this is only 15% wind penetration. What we found in more simulations is higher penetration of wind participating will actually lead to even better response. Okay, so when we did these grid simulations, we were very excited. But one thing we had worried about is we're asking our wind turbines to respond to these power reference requests and possibly asking them to pitch more and do more. We were worried that that would lead to larger structural loads, and so we thought that that might end up being the cost of providing the service. But it turns out that in general, the structural loads are actually decreased. Because in general, so most of the time, you're going to be operating at a derated operation. So you're going to have lower loads than usual. And then only occasionally, when these events occur, are you asking then for more.
So at maximum load, when you understand maximum load, you have the optimal angle of attack where you get maximum lift, and then and that also means maximum force, maximum force structure, and you back off from that.
We back off a little bit, so we have lower loads in general in that derated operation. And only when we're responding to events are there occasionally slightly more loads. Yeah, Frank?
Yeah, but I'm a pretty grid operator, and I want to get paid for every watt I can generate.
Yes, so that's an issue, right? So you derate to 90%, you're going to get less revenue for the power production. And so this is definitely an issue going forward, because right now, generating sources are not paid for providing responses to grid events. And so in the future, I think the incentive should be that they are paid for providing the service. Yeah. And then that could then even it out economically.
I have a similar question. Do these droops actually happen often enough that it's justifiable, like you were saying, to derate your wind turbine full time so that you can kind of compensate for these droops?
So that's another good question. So you could try to predict when there might be a peak demand. And so you might run, say, closer to maximum power most of the time. But and then if you predict that you might need that headroom, then you derate. So you're only then derated for some shorter amount of time before events.
Wouldn't the more appropriate question be, we're trying to prevent the catastrophe. When we have a catastrophe, we have a blackout, I want to remember New York City years ago, the cost of that catastrophe to the nation is huge. It's humongous. When that lead peak drops a little further down, it's catastrophe and a blackout. The wind energy can prevent these blackouts. That cost, of course, you need to make the politicians understand that I realize that that cost is incredible.
Jake?
So if you were derating all the time, would that also allow you flexibility to participate in the regulation market?
Yeah, definitely.
Right. So you said that generators don't get paid for this, but like in the big ISOs.
Okay, so they don't get paid for primary frequency control, as far as I understand. But for regulation services, they can get paid.
And regulation services
Provide the secondary, right? And that's all, yeah.
I mean, since those numbers are available, right? I mean, you can look at at PJM and see what the numbers are. You know, you could. So here you're trading headroom for the length of time over which you can. You know, I mean, if you have a little bit of headroom, right, that doesn't cost you very much, but then you can't push very long. And if you have more headroom, you can push for a longer time. So if you look at
so that trade-off, right, exactly. And I think I have that as an area of future work to kind of evaluate what is the proper market incentives here. Frank?
Well, the integrated storage numbers, we get paid for any ancillary service. And in general, in the regulated utilities where they can provide everything, those are just assumed as part of the overhead. And when you go to dividing up the industry, you pay transmission, you pay for this and that different separately, then this becomes a big commission, big economic issue. So that whole area there. And let's see, Kevin Doran and some of the others spent a whole study looking at that market if you're interested.
Okay.
Problems of ancillary service.
Yeah.
Or also, so there's a source for you to look at that.
Okay, great. Thanks. All right, so moving forward. So I just showed some grid simulation results. We have done detailed wind turbine response results as well to assess what are the typical structural loads that are incurred when providing derating and providing primary frequency response and secondary response. And so we use NREL's codes to help us evaluate wind turbine response. These codes are freely available to anyone that wants them. So they have a TurbSim code that generates realistic wind fields, which we can then pass through the wind turbine in another code known as FAST for fatigue, aerodynamic structures, and turbulence that simulates the turbine response with medium fidelity. There's a nice interface through MATLAB Simulink to enable us to test out different controllers relatively easily. We haven't used this newer code, which is a simulator for offshore wind farm applications. It's a much higher fidelity, much more computationally intensive code, but it actually simulates the wakes and the interactions among turbines on a wind farm. And ultimately, we would like to test that out at the wind farm level. So besides the primary frequency control work, we have done some secondary regulation work, and we have actually had the opportunity to implement our active power control algorithm on the three-bladed 600 kilowatt research turbine at NREL. So NREL is just south of town here, this Wind Technology Center. There are 4 megawatt wind turbines, and there are 2 what are known as CARTs, Controls Advanced Research Turbines. And we, last wind season, got to test out our active power controller on this wind turbine. This season, we're testing it out on this turbine because there's additional instrumentation there that will allow us to measure winds upstream approaching the wind turbine. So to show some of our results, so maybe before I get to that, so we've changed the way that wind turbines are controlled. They're not always trying to maximize power, so we've completely changed the controller for them. And so we have done a stability analysis of some portions of our new controller. And we have, as I mentioned, also looked at secondary control. We've combined the primary frequency control with secondary control methods, and we did field test last season on the CART 3, and so these are actual experimental results. Ideally, the grid frequency deviation is 0. Okay, we actually take frequency data from the ERCOT, the Texas grid. So these are actual frequency, grid frequency data that we use as input to our controller, and so then this grid frequency will generate a power command. Okay, so for the CART 3, this is the rated power, okay, and at some point, so you might say that we maybe can predict some event about to occur, so we derate, okay, by 90%, or derate down to 90% of rated power, and then when the grid event actually hits, it asks for more power to try to balance the grid event. And so this generated power actually follows the commanded power quite well, okay? And so in this coming season, we're going to be testing on the other wind turbine using some additional instrumentation and using some modifications to the control algorithm. So in terms of ongoing and future challenges, What we've been looking at so far is active power control of a single wind turbine. How can we control a single wind turbine through the pitch control and the generator torque control to follow essentially arbitrary power reference commands. Ultimately, we'd like to expand this out to the wind farm level, to the wind power plant level. So if a wind farm receives primary frequency control commands and secondary power commands from the grid operator, then how do we take that overall wind farm power command and divide it into all the individual wind turbines on the wind farm? It's probably not going to be just the total power command divided by the number of turbines, because the wind turbines actually do interact through their wakes. So if the lead turbines take out a lot of power, then they generate a wake, and that leads to more turbulence, more structural loads on the rear turbines, and there's also less wind power available for the rear turbines to capture. And so we need to better understand how wind turbines interact with one another to actually appropriately divide out that power reference command to the wind farm to the individual turbines on the wind power plant. So there has been work by systems and controls researchers looking at coordinated control of arrays of wind turbines on a wind farm to try to maximize power capture, which has been more of the work, but also to some extent to try to minimize structural loads on wind turbines. And so this is a very complex problem, and a lot of these initial algorithms that have been developed use very simplified models of the wake interaction among the turbines. And so going forward, we need to understand that better and incorporate that knowledge to improve the distributed or coordinated control of wind farms. As we get to expanding to active power control of wind farms and wind power plants, taking into account the wake interactions, there are questions of, how do we derate the different wind turbines? We might not want to all derate them to the same level. So how do we decide that? And how do we, divide up that power reference command coming in to the different turbines? So in summary, as there's higher penetrations of wind energy on the utility grid, motivates active power control of wind turbines to actively control the power output to meet grid requirements. And we found that wind turbines can enable a faster response to frequency events on the grid, that dynamic droop curves are possible for wind turbines, and that allows wind turbines to really provide this faster response and at the same time not necessarily have increased structural loads. And we found through numerous simulations that if we have higher penetration of wind, higher levels of primary frequency control participation of the wind power plants, and more derating, that all these factors tend to improve the grid reliability and the grid response. So we are continuing to carefully evaluate any cost of providing this service by carefully looking at structural loads through both simulation as well as our experimental implementation on the research turbines at NREL. And as already mentioned, right now, at least for primary frequency control, there's not the proper market incentives in place, and that should be established. And that is, I think, an area that many systems and controls researchers would probably be interested in investigating. So other areas of future work is to, so far what we've looked at is active power control of wind turbines and what can we achieve by doing that without looking at demand side management or storage. So obviously we can combine active power control of wind power plants with storage capabilities and look at what could be achieved using both of those, and possibly looking at the combination of all three, apply active power control, storage, and demand side management, and look at the reliability of the grid that could be achieved from that point of view. And of course, there's active power control of solar power plants. That's actually a newer area of research, and less has been done there, and I think a lot could be done as well, and can look at the combination of active power control of solar power plants with wind power plants, with demand-side management and storage and look at the increased reliability of the grid that could be achieved that way. So with that, I'd like to just acknowledge our sources of funding and collaborators. In particular, Paul Fleming at NREL has been a primary collaborator on this active power control work. I've had a number of great students working in the wind energy area. Jacob Aho and Andrew Buckspan are the two students currently working in the active power control area. And so with that, thank you.
So this is only looked at just the horizontal axis.
Yes. Yes. Okay.
What's a typical time constant for being able to implement your active control on one under pitch and the other one under torque? What are the time constants for being able to?
So on the generator torque, it can respond in milliseconds. And the pitch is on the order of seconds or tens of seconds.
Because that kind of limits how fast you can respond.
Right. Okay. Yeah, Mark?
So when you showed the droop curve of the conventional generator, it looked like it went up to 25%. Okay, so if you wanted to be able to deliver that, you would have to operate at 75% of.
In order to have that headroom, correct.
Is there some conventional reason why,
Yeah, how do you set your D rating?
I mean, like, so in a typical transient event, right? Some generator, there's some breaker, there's some fault on some line, some breaker closer to something, right?
Right.
So then all these generators have to make up for this, the guy who is now no longer connected.
Right.
And how hard do they have to push?
So
Are 25% excursions,
well,
frequent? Is that like once in 100 years?
yeah, it depends on the grid, and it depends on sometimes natural events and things like that. And can you predict some of that?
So like these big cascading blackouts are sort of like, let's say that's not part of the discussion.
Yeah. And so that's and then the whole market incentives and things like, at what level do you derate that you're running at on a regular basis, right? So you're losing that lost opportunity of production there.
The guys who do generation must have like statistics.
Yeah, and I don't have that. At least I've seen little bits and pieces, but
He's asking is for the population of the world, to look at this for the population of the world map. Okay, and it's the amount of blackout is minimal. Right, so you're looking at why even do this?
No. I mean, there are real reasons why you want to keep the frequency stable, right? So my question is, like the U.S. has, I don't know, like a few hundred gigawatts online at any given time. So gigawatt per generator. I mean, there's like maybe a few thousand generators in the U.S. that are spinning at any given time. So if you went in and looked at their like control signals, right, or how much they're delivering compared to what they were scheduled to deliver, or like how much they're delivering compared to what they were delivering a few seconds ago. How big are the excursions?
They're not the last time I read, but this here, where this really is going to mean something is as the world population, unfortunately.
You never know when the blackout is going to come. So
right.
you can't say, well, like we're going to derate because we think the blackout is coming.
No, I'm not saying that's not true. She's not saying that's the technology. That technology becomes more important as the people in the world start multiplying and multiplying, because there's less and less traditional power plants that you will need because of the pollution, etc. And that's how they can make use of them.
Right, so the wind penetration will increase as population goes up and sustainability becomes more and more required. I get that, right? But how much excursion do you need? Suppose you had 100% wind, right? How much
yeah. So here, what we were looking at is, what's the capability of wind? If you derate to some level, and so then the question is, is what level do you set it at in practice? Yeah.
So my question is, these other guys have been providing it historically as kind of a free benefit, right? Since you have
They're spinning.
Yeah, in their
Sure,
setting, you've
right.
got controls, and so it'd just be useful to know to what extent it was called on. And then if you said, okay, we'll build an all-wind grid that can be called on to that extent, it can.
Okay. All right, thank you. Thank you again.